Okay, so in this video we're going to look at CC11, which deals with metals, the reactivity of metals, and how they are extracted. What we have to remember when we're talking about metals is they're not something that they're not made in the lab. They do all occur naturally. But metals are reactive and they will react with the other elements around them, which means when you find them, you're not going to find them as the pure metal. They will already have reacted with the other elements around them. And what I've got here is a list of metals with the most reactive at the top that we need to know about, potassium at the top, and then down at the bottom I've got silver and gold, which are the least reactive metals. Also in my list I have got carbon and hydrogen, which are not metals at all, and I'll explain why I need them in a moment. Okay, so you've got a list of metals. Okay, these guys are all on the left hand side of your periodic table, most reactive at the top, down to the least reactive. Okay, and all of these guys up here at the top, potassium, sodium, lithium, because they're so reactive, even though they occur naturally in the environment, you're not going to find pure potassium or pure sodium or pure lithium naturally in the environment, because they will have reacted with other elements around them, particularly oxygen. Okay, because they've reacted and you can't find them as pure metals, you need a method to extract them. Okay, so if you had potassium oxide, how can you extract or get back the potassium from the potassium oxide? If you had iron oxide, which is the same as rust, how can you get iron back from the iron oxide? Okay, so that's what we're going to be looking at. We're going to look at how to extract these metals after they have reacted so that we can get the pure metal back. Okay, and there are 4 different extraction methods we need to know about: electrolysis, which we already looked at in CC10, reduction with carbon, which we're going to look at now, and then 2 biological methods, phytoextraction and bioleaching. And we use this reactivity series to decide whether we should use electrolysis or reduction with carbon. They're the 2 main methods, and we use this reactivity series to decide. Okay, so the reason I've got carbon in here in my reactivity series is because all the metals above carbon I have to extract with electrolysis, and then the metals I've got here below carbon I can extract using reduction with carbon. So knowing where carbon sits in this reactivity series is very important. Okay, you don't need to learn the whole reactivity series, but you do need to know where carbon sits. It's below aluminium and it's above zinc, and you need to know that so you can predict whether you're going to be using electrolysis or reduction with carbon. Okay, silver and gold down at the end typically don't need to be extracted because they're unreactive. You can find them as pure metals. Okay, so we're going to focus in on this one, reduction with carbon. What exactly do I mean by that? And I'm going to give you an example chemical reaction. Okay, so I'm going to take zinc oxide. So zinc is my metal, but it's reacted with oxygen and it's formed zinc oxide. I want to get the zinc back from the zinc oxide. So what do? I react it with carbon. Okay, because carbon is more reactive than zinc, okay, I've got carbon here above zinc in the reactivity series. Because carbon is more reactive than zinc, carbon and zinc can swap places. And when that happens, carbon ends up bonding with oxygen. And instead of writing carbon oxide, I'm going to write carbon dioxide because that's what will form. And then zinc takes carbon's place. So zinc is left by itself. Okay, so I've taken my zinc oxide and I've reacted it with carbon, and my product is pure zinc. So pure zinc metal is the product of this reaction. Okay, if I were to take iron, the same thing would happen. Okay, I have iron oxide. Okay, I react it with carbon, and because carbon is more reactive than iron, okay, it's higher than it on the reactivity series, iron and carbon can swap places. Carbon bonds to the oxygen and you get carbon dioxide, and then you get pure iron by itself. Okay, now if I were to try this exact same thing with something above carbon on the reactivity series, I'm going to try it with magnesium oxide. Got magnesium oxide and carbon. Okay, in the above reactions I just swapped carbon with the metal. Okay, but I can only do that when carbon is more reactive than the metal. So carbon was more reactive than zinc, so it took its place. Carbon's more reactive than iron, so it took its place. But carbon is less reactive than magnesium, okay? So it cannot take its place and you get no reaction, okay? So in this example here, magnesium and carbon do not swap places because carbon is less reactive than magnesium. It can only take the place of metals that it is more reactive than. Okay, so this tells me that I can use this technique, which is called reduction with carbon, on all of the metals below carbon, like zinc and iron and copper, but I cannot use it on the metals above carbon. Because I can't use reduction with carbon, I need a different method. I need electrolysis. Okay, so they could ask you, which method would you use to extract magnesium? And you would say electrolysis. And they might ask you why. Okay, so you would write there that carbon is less reactive than magnesium. So carbon cannot displace magnesium. And by that word displace, I just mean carbon cannot take magnesium's place. Okay, so that's how you would explain why that reaction does not take place. Carbon is less reactive than magnesium, so carbon cannot displace magnesium. Because this reaction doesn't work, you need electrolysis instead. Okay, the last thing I want to mention is the fact that I've called this technique reduction with carbon, and we've come across that word reduction before. We learned about oil rig. Oxidation is loss, reduction is gain of electrons. Okay, but in this topic, we actually have an even simpler definition of oxidation and reduction. And oxidation is just the addition of oxygen, and reduction is the removal of oxygen. And when you look at these equations, you need to see what is being oxidized and what is being reduced. And this is easier to spot because rather than having to figure out what's happening in terms of electrons, you can just see what is gaining oxygen. So if I look at my first equation here, zinc oxide plus carbon goes to carbon dioxide and zinc, I need to see what is gaining oxygen. I need to look at my starting reactants and ask myself which one of these does not have oxygen on the left-hand side of the equation. So what is starting without oxygen? So you can see zinc oxide, that's zinc and oxygen, but you've just got carbon by itself. So carbon is starting without oxygen. But when I look at my products, carbon dioxide, carbon does have oxygen. So carbon has no oxygen at the start of the reaction, carbon has oxygen at the end of the reaction. So I can say that carbon is oxidized. Okay, because it's gaining oxygen going from the left to the right. The equation underneath is exactly the same. Carbon starts off with no oxygen and it ends up as carbon dioxide. So again, carbon is being oxidized. All right. And then the other thing we need to look at is what is being reduced. What has oxygen on the left, but then doesn't have oxygen on the right. Okay. So zinc oxide, you've got oxygen there with zinc. And then on the right-hand side, it's just zinc by itself. Okay, so I can say that zinc oxide is being reduced. Zinc oxide is losing oxygen. Okay, so make sure you get this right. Okay, it's not zinc that's being reduced, it's zinc oxide. Okay, zinc cannot lose oxygen because zinc does not have oxygen, but zinc oxide can lose oxygen because zinc oxide has oxygen. So it's the zinc oxide that's being reduced, okay? And here you've got iron oxide going to just iron. So the iron oxide is being reduced. You're taking that oxygen away from iron oxide, leaving you with just iron, okay? So I'm going to give you an equation to do for yourself. So I've got copper plus carbon. And I just want you to complete this word equation, and then I want you to tell me what is being oxidized and what is being reduced. So press pause, complete the equation, and tell me what is oxidized and what is being reduced. Sorry, that should be copper oxide plus carbon. So now press pause and complete the equation. Okay, so your equation should look like this. Okay, carbon, if we look up here, is more reactive than copper, so carbon can take copper's place. So carbon and copper are going to swap places, leaving you with carbon dioxide and copper by itself. Copper oxide is losing oxygen. You're going from copper oxide to copper, so copper oxide is losing oxygen. So I say copper oxide is reduced, and then carbon, once again, is gaining oxygen. I can say carbon is oxidized. Okay, so that's reduction with carbon. Make sure you can complete those equations. Make sure you can identify what is oxidized and what is reduced, and make sure you are aware that this technique only works on the metals below carbon. For all of the metals above carbon, you're going to need electrolysis. And this is your reason. Carbon is less reactive than whatever metal, so carbon cannot displace whatever metal. Okay. The other two techniques, extraction techniques, are called the biological techniques. You've got phyto extraction and you have got bioleaching. Just need to know what they are and then advantages and disadvantages of both. Okay. So in phyto extraction, this is a plant, by the way. In phyto extraction, what you do is you plant, you put plants in the ground, and what the plants can do is their roots obviously go down into the soil, and if you have got lots of metal ions in your soil, so for example if you've got copper ions in your soil, okay, so these aren't lumps of metal, they are ions, and they are dissolved in the water in the soil. And your plants, if you plant your plants on soil that contains lots of metal ions, what can happen is that the roots of the plant can absorb those metal ions into the roots. Okay, and once you've got all of the metal ions in the roots of the plants, you then harvest the plant. Okay, so you burn the plant to harvest the plant, and you can then extract the metal ions from the ash. Okay, so you are going to, plants can absorb metal ions, and you have to say metal ions, okay, because they're not going to absorb solid pieces of metal. They have to be in ion form. Plants absorb metal ions, and then plants are burned to collect the ions from the ash. Okay, so that is how phyto extraction works. In your little core revision booklet, I've given you, yes, an advantage and a disadvantage there of phytomining or phyto extraction. Okay, so you can use low grade ores, so you can get metal from quite low quality ores, and because you can get metal from low quality ores, that means you don't have to go out mining to find new ores if you can use the ores that you've got. But phytomining is actually expensive. I know it sounds like it would be a cheap method, just planting a few trees or whatever, but a lot of people need to be employed to do the planting, take care of the plants, and then harvest them and burn them and then harvest the metal ions from the ash. There's actually quite a lot of people are employed, so it's not a cheap method. Okay, so that's phytomining. Then the other biological method is bioleaching. Okay, and in bioleaching you are using bacteria. So that is why they're called the biological methods. You've got plants in phyto extraction, you've got bacteria in bioleaching. And what the bacteria does is the bacteria can break down ores and turns them into solution. Okay, so it gets the ore into a liquid form. Okay, and once it's in a liquid form, you've got lots of metal ions floating around in liquid form. You can extract the metal using displacement. And by displacement, I just mean similar chemical reactions to the ones we carried on down here. Okay, so you break down the ores using bacteria, you get them in solution, you've got metal ions floating around in solution, and once you've got those metal ions in solution, you can extract them using displacement, similar method to what we would have used down here. Okay, again, advantages and disadvantages of bioleaching. Advantage, same as the advantage of phyto extraction, you can use low-grade ores, but the disadvantage is it does release toxic substances into the environment. Okay, so know what phyto extraction and bioleaching are, know their advantages and their disadvantages. So we've looked at how to extract metals, but now we need to have a look at some of the chemical reactions that metals can undergo. And one of the most important ones is the reactions of metals and acids. Okay, so we've looked at the reactions of acids and bases. Now we're going to look at the reactions of metals and acids. And just like when an acid reacts with a base, when an acid reacts with a metal, you form a salt. But with a base, you form salt and water. And when an acid reacts with a metal, you form salt and hydrogen gas. And the naming of that salt is exactly the same as it's always been. So I've got an example here. Calcium is my metal. Sulfuric acid is my acid. To name the salt, I take the name of the metal, which is calcium, and then it ends in sulfate. Okay, so sulfuric acid will end in sulfate. If you used hydrochloric acid, it would end in chloride. If you use nitric acid, it would end in nitrate. So we name the salt exactly the same way we did in the acids topic, but instead of getting water, you are going to get hydrogen gas. Okay, I want you to have a go at 3 of those for yourself. Okay, so press pause and complete the equations. You need to be able to name the salts, and then it's always plus hydrogen, plus hydrogen, plus hydrogen. Okay, it's not plus water. It would be plus water if you had a base here, but you've just got a metal, so it's just plus hydrogen. Please press pause and complete those equations. Okay, so I've got the answers here. The name of the salt in this case would be magnesium sulfate. Here it would be copper chloride. Here it would be iron nitrate. So these are the 3 acids that you need to know, and you need to know the salt endings for both. Sulfuric is sulfate, hydrochloric is chloride, nitric is nitrate. And then other than that, you're just taking the name of the metal and you're putting it as the first word of the salt. In each case, you are forming hydrogen gas. Okay, so if you were to actually carry out these reactions, what would you see? Okay, because you're producing hydrogen, which is a gas, you would see bubbles. Okay, and if you wanted to confirm that that gas was hydrogen, you would take a lit splint, you would insert it, and you would get a squeaky pop. Okay, but you would see bubbles if the gas was hydrogen. Okay, now if I come back over here to my reactivity series, okay, I put the metals in order with most reactive at the top and then least reactive down the bottom. And you'll see that you've got magnesium up here, and you've got copper right down the bottom, and you've got iron in the middle. So if I were to carry out these reactions with the 3 different metals, I would expect magnesium, its reaction to be the most reactive, and I would expect copper to be the least reactive. So what am I actually going to see? How can I see that magnesium is more reactive than copper? Okay, well, if they're both producing hydrogen gas, they're both going to produce bubbles. And the easy way to see which is the most reactive is by just looking at how many bubbles are produced. So because magnesium is the most reactive, I would expect to see lots and lots of bubbles when magnesium is reacting with an acid. Copper is much less reactive. I would expect to see a lot less bubbles. So the one that's producing the most bubbles is going to be the most reactive metal. If I wanted to quantify that, so sometimes it might be harder to tell which is producing the most bubbles. Like if there's lots of bubbles being produced, it mightn't always be obvious which is the most reactive. So if I wanted to quantify that, if I was doing this reaction in a test tube, okay, and I've got my acid in the test tube and I drop in my piece of metal and I'm going to start to see lots and lots of bubbles as they react, what I could do is I could collect all of that gas. So I need to put a little tube in there, okay, to collect that gas. And then I could connect my delivery tube to a syringe, to a gas syringe, okay. That would tell me the exact volume of gas being collected, okay. So if I connect my test tube to a gas syringe, then that gas syringe will collect all of the hydrogen gas that's being produced, and then I can compare. So this experiment, I might see that I've got at the end 20 centimeters cubed of hydrogen gas. I could do the same reaction with a different metal and see that I'm only collecting 5 centimeters cubed of hydrogen gas. Okay, so it allows me to quantify and put actual numbers on it and show that one metal is more reactive than the other. Okay, so know your reactions of metals and acids. Know that you're producing hydrogen gas, that you're going to be seeing bubbles. The more reactive the metal is, the more bubbles that will be produced. And if you actually want to measure how much gas is being produced, you would attach a gas syringe. Okay, one more thing that we need to take a look at, and that is the same reactions as I've just written out above, but we need to be able to write them as Ionic equations. So we're going to have a little bit of practice on this because I appreciate it can be a little bit tricky. Okay, so I've written out a reaction between a metal, sodium, and an acid, hydrochloric acid, forms a salt, sodium chloride, and hydrogen gas. So that's my word equation, and underneath that I have written my symbol equation. So sodium is just Na, hydrochloric acid is HCl, NaCl, sodium chloride, and then hydrogen is H2 because hydrogen is diatomic, so I always write it as H2. And I've balanced it, okay? And I'm now going to turn this symbol equation into an ionic equation, okay? So when I'm writing it as an ionic equation, okay, I need to be including my charges, all right? So when I am doing this, okay, first question I need to ask myself is it an element or is it a compound? Okay, so sodium by itself here, it is an element. Okay, so I'm going to put an E over it. HCl here, HCl, there's two different elements that have reacted, so that is a compound. NaCl, that is also a compound because I've got two different elements reacted together. And then H2, you've only got hydrogen, and hydrogen is an element. Okay, so essentially, if you've only got one capital letter, it's going to be an element, and if you've got two capital letters, it's going to be a compound. Two capital letters tells you you've got two different elements. If you've only got one capital letter in your formula, then it's an element, okay, even if there's a number like it is here in H2, okay? So if it's an element, I don't write it with a charge. So I just write sodium as Na with no charge. But if it's a compound, then I have to write each individual ion separately with their charges. So if I have HCl, what ions do I have in HCl? Okay, HCl is an acid, and we know that all acids produce H+, and in this case, I will also have Cl-. On the other side of my equation, I've got NaCl, and this time it is a compound, okay? NaCl is a compound, so I need to write the ions that are present, okay? Sodium is in group 1 and always has a +1 charge. No matter what it's bonded to, sodium is always +1. Chlorine's in group 7 and always has a -1 charge every single time. Hydrogen is an element, and if it's an element, I write it exactly the same way as I did before, and I do not include any charges. All right, so you'll be given the symbol equation, and you need to turn it into an ionic equation. If it's an element, then you don't do anything. You write it exactly the same as it was above, but if it's a compound, you need to split that compound into its ions. So HCl, acids always give you H+, that's where I'm getting the H+ from, and then I'm getting Cl- because chlorine is in group 7, and if it's in group 7, it always has a -1 charge. Then I've got NaCl, Na is in group 1, so it's got a +1 charge, and again, Cl is in group 7, so it's a -1 charge, okay? Once I've it all written out like this, if there are any ions that are exactly the same on both sides, then I just cross them out. So Cl is exactly the same on both sides, okay? I've got sodium on both sides, but on one side it's plus and on the other side it's neutral, so I can't cancel them out. I can only cancel them if it's exactly the same on both sides. And then I write down what I'm left with. Na and H+ goes to Na plus H2, okay? To balance that, I've got one sodium on each side, so it's already balanced. But I've got two hydrogens here, so I need a big 2 here, and I got Na plus 2H plus goes to Na plus H2. Okay, so I've written another equation underneath. This time I'm using the metal aluminium, and I'm still reacting that with hydrochloric acid, and I'm forming aluminium chloride and hydrogen. Okay, you'll be given the symbols, all right? First thing I need to do is see, is aluminium an element or is it a compound? Okay, aluminium by itself is an element. Okay, I've only got one capital letter there. That's a lowercase l. So one capital letter means it's an element. HCl, again, compound. I've got two capital letters, which tells me I've got two different elements, hydrogen and chlorine. Here, again, I've got two different capital letters. I've got aluminium, capital A, and chlorine, a capital C. Two different elements, so it's a compound. And then here, H2, it is an element. I've only got one capital letter. If it's an element, then I write it exactly the same way underneath. So I'm still writing aluminium as Al. I'm not changing. But if it's a compound, I need to split it up. It splits up into H plus and Cl minus, just like it always does. And then over here, I've got aluminium and chlorine, and I need to split this up. All right. Aluminium is in group 3, so it always forms +3 ions. Okay. It doesn't matter what it's bonded to. It will always be Al plus 3. And then I've got chlorine, all right? And I know there's a 3 here, and that might get confusing, but chlorine's in group 7, and it always forms -1 ion. So I don't care that there's a 3 there. It's chlorine, it's in group 7, it's forming a -1 ion. It always forms a -1 ion. And then I've got hydrogen, which is an element, so I don't change. I leave it exactly the same way, All right. Again, I've got 2 chloride ions on each side, and I can just cross them out. They're exactly the same on each side. And then I'm left with Al plus H plus goes to Al plus 3 and H2. Again, to balance this, I'm going to put a 2 here. All right. So it's exactly the same as the one above. The fact that there was a little number in the formula didn't change a thing. I'm going to do one more for you, and then I'm going to get you to do some. Okay, so same situation here. Magnesium by itself is an element. HCl is a compound. MgCl2, I've got 2 elements there, so it's a compound, but hydrogen is just an element. If it's an element, it stays exactly the same, so I would still write magnesium as just an Mg. The compound, I need to split up into its ions. I'm going to get H plus, and I'm going to get Cl minus. I need to split this up into its ions to look at what those ions will be. I find magnesium on the periodic table. I see it's in group 2, so it's always got a +2 charge. And then I find chlorine on the periodic table, and I see that it's in group 7, so I know it has a -1 charge. And I ignore that little number 2 next to chlorine because it's not going to affect my charge. Okay, I've got Cl minus. When it was bonded to magnesium, it was Cl minus on the previous page when it was bonded to aluminium, and it was Cl minus when it was bonded to sodium. It's always Cl minus. Don't be put off by the numbers. And then H2 is an element, so if it's an element, I don't change it at all. The chlorines, once again, are cancelling, and I'm left with Mg plus H plus goes to Mg plus 2 plus H2. And I put a 2 there to balance it. Okay, so try and do these to yourself. Okay, lithium and hydrochloric acid and calcium and hydrochloric acid. I'll just tell you, lithium is in group 1 and calcium is in group 2. Try and do what I have done for those 2 equations. Press pause, have a go, and then press play. Okay, so the first one should work out as Li plus 2H plus goes to Li plus and H2. Okay, lithium is an element, so I don't put a charge on the left-hand side. I split up my HCl into H plus and Cl minus. On the other side, I've got a compound, so I'd split them up. Lithium's in group 1, so it's got a +1 charge. Chlorine's always -1, and then I don't split up my H2 because it's an element. I can cancel my chlorines, and this is what I'm left with. In the next one, again, calcium's an element, so I don't put a charge in it. I split this up into its charges. Calcium chloride, it's a compound, so I do put charges on it. Calcium is in group 2, so it's got a +2 charge. Chlorine's always got a -1 charge. Plus the H2, the chlorines cancel, and this is what I am left with. There are a couple of practice questions in your core info guide. So this topic is on page 25. So if you want more practice with this kind of thing, do the practice questions on page 25. All of the answers are on page 26 and 27.